The next example I want to look at is the function f of x equals sine of x. Let's find the Maclauren series of this. So we're going to do the same thing we did last time and create a table and try and find the derivatives here. So what can we do? Okay, so we have k. Right, we have the kth derivative of x. Okay. We have the kth derivative of f at 0. Did I say the kth derivative of x? I meant of f. Right? So let's start working with this here. So we get 0, 1, 2, 3, 4. All right, we'll take more if we need. So here, the original function is just sine of x. The derivative is cosine. Then the second derivative is negative sine. And the next derivative is negative cosine. And then we're back to sine. Right? So let's plug in x equals 0 to each of these. We're going to get 0, 1, 0, negative 1, 0. That pattern might not be too obvious yet, so let's take a few more. 5, 6, 7 here. Right? So this is just going to be cosine minus sine minus cosine. Right? And you can see it's just going to repeat from here. So this should be enough. Right? So here we're going to get 1 and then 0 and then negative 1 again. So this sequence, what it does is it goes 0, 1, 0, negative 1, 0, 1, 0, negative 1. Okay? So getting a general term, getting a general CK here is going to be a little difficult because there's not really a formula we can write for this. So if you ever run into a situation like that, one of the best things we can do is actually just write out the Maclauren series piece by piece. Don't try and write it with sigma notation yet. Right? So what do I mean? Right? So sine of x, we want to literally write this out. Right? Literally write exactly this. C3 x cubed plus c4x to the fourth, and so on. Right? Just literally write these terms out. Okay? So let's go ahead and do that. So knowing what we know, right, we're going to get 0 plus c1 is just going to be 1 over 1 factorial. So let's write that, 1 over 1 factorial x, and then plus c2 is 0. Right, so plus 0x squared, then plus negative 1 over 3 factorial, x cubed, plus 0x to the fourth, plus 1 over 5 factorial, x to the fifth, plus 0x to the sixth, right? And so on. Okay, so once we kick out all the things that are just 0, this is gone, this is gone, this is gone, this is gone. Once we kick all that stuff out, let's look at what survives. 1 over 1 factorial, x, minus 1 over 3 factorial, x cubed, plus 1 over 5 factorial, x to the fifth. And we didn't actually write it here, but we know that 7 here is negative 1. So we're actually going to get negative 1 over 7 factorial, x to the 7. All right, and this pattern will continue. But now if we look at this, we have some kind of a pattern going on. All right? So what we can do here is if we try to start this at 0, all right? If we start it at 0, then what we notice is we have an alternating series, right? It's positive, negative, positive, negative, positive, negative. So we're going to have a negative 1 to the k because we're starting at 0 and we want the first term to be positive. Negative 1 to the k will do the job, right? Now let's look at the factorials on the bottom. They're odd numbers that get progressively larger. So this is going to be 2k, and if we want to start at 0 here, we need to write 2k plus 1 factorial. Right? And notice the number down here matches the power. We can even put the 1 there if it helps. The number in the factorial matches the exponent on x. So this should be times x to the 2n plus 1. Right? This is, right here, the power series, the Maclauren series representation of sine of x. Hopefully that's pretty interesting. I think it's pretty interesting that we're able to represent functions like sine and e to the x as infinite polynomials, right? They're polynomials of infinite degree. So they don't end, but we're able to represent these complicated functions as simple things.